Hello, my name is Francis Guillier, and I am a technical product manager at VMware working on cloud-native apps infrastructures. I will be your presenter for this session about Kubernetes. The objective is to introduce the technology so you get a basic understanding of the open source project and its key core components. This presentation is mainly designed for people who just start their journey learning about container orchestration technology. A bit of knowledge around Docker will be useful, but this is not a prerequisite. Kubernetes is today one of the most popular platforms in the cloud-native app space, so it's definitively worth investing some time and energy on it. Let's get started. This is the agenda for the session, and it is composed of 4 major pillars. We will start with reasons industry needed such a product like Kubernetes. Then we will introduce Kubernetes itself by explaining its role and capabilities. The remaining of the presentation will be focused on Kubernetes architecture / components and Kubernetes basic concepts, or in other words, Kubernetes objects and primitives. Why Kubernetes? Before that, let's first address the question, why containers? Traditionally, one or many applications are installed in a VM, and they all share a common set of libraries, tools, and softwares maintained and managed by the system administrator. As shown on the screen at the bottom left, we have a WordPress and Apache application running in the VM. While this type of configuration has been working well for years, one of the major drawbacks is the strong dependency between the installed application and the available libraries, tools, and software on the VM. Every time a new application needs to be installed in this VM, developers need to double-check the libraries are compliant with the code. If the new application requires a new set of libraries or latest version of the library, system administrator and developers need to figure out if upgrading the libraries would impact existing running applications. Sometimes the situation may even be worse, like in case of software application upgrade. If the new version of the application needs the latest release of particular library, well, we come back to the previous tricky problematic. As you can understand, having fixed versions of library, tools, and software inside the operating system that must be shared across multiple applications running above somehow locks developers with installing new software or even easily upgrade existing one. Here comes the container technology. In the VM displayed on the bottom right side, we have now a minimal Linux OS with its kernel and Docker engine installed on top of it. This minimal OS can be Photon OS, which is developed by VMware. Container is an operating system virtualization technology that leverage existing Linux kernel built-in codes like namespace, cgroup, and capabilities to run a set of completely isolated processes inside VM, which behave now as a container host. The Docker engine, or more globally speaking, the container engine, is a key component to be able to run those containers inside the VM. By using a simple command like docker run name of the image, we can quickly instantiate a new container running inside the environment. The Docker engine will pull the image from a public or private registry, and once completed, it will start the container. Typically, a container does not boot up or reboot. They just get started and this is usually fast, i.e. in magnitude of milliseconds or seconds, depending on the embedded application. But how is container image created? If Docker is used, the response is by using a Docker file as shown in the upper right of the screen. A Docker file contains a set of instructions to build the image, like run command to execute OS-related operations, auth to set environment variables, expose to specify which network port the container will use, and CMD to characterize the main process the container will run when started. Each line of instruction in the Docker file will create a specific file layer of the image. The overall image is a composition of all these file layers. Maybe the most important instruction in the Docker file is the first one, which contains the from keyword and dictates the base image to be used when building the desired Docker image. In this case, we specify Ubuntu 12.04 as the base image. The declaration may be confusing, but Docker is not going to pull the whole Ubuntu OS binary. It is going to simply use tools, leads, and software provided by the base Docker image. Please keep in mind that container does not have a base operating system. Container is by definition an isolated process running on top of the operating system provided by the container host. It happens here our container host is powered by a Linux distribution which is PhotonOS. The CMD instruction specifies Apache 2 as the main process for this container, and as such, when the container is started, you will see one process running in the container. Best practice with container technology is to run only one process per container. Our container is now fully self-sufficient. It has its own tool, libraries, and software. And it has its main process. On this container host, now we can run multiple containers, each one completely isolated from the others. As shown here, a second container running WordPress can be started and using its own set of tools, libraries, and software. Even the base image can be different. The second container is indeed running Red Hat as base image. Each container has its own life cycle and operates independently of the others. They can be upgraded separately, and code or libraries used by a container can evolve over time without impacting the neighbor container. As a fun fact, we can say that what happens in the container stays in the container. One point to remember is that container images are immutable, which means the content cannot be modified on the run. To modify a container image, user has to modify the Docker file to build a new image. Typically, container images are versioned and keep track of incremental changes between the different releases. Creating and running containers in development phase is quite straightforward, as requirements to operate this container are quite relaxed. Developers just need to make sure their package code runs as expected and fulfill the desired expectations. Development is done using personal laptop or single server, which constitute a super simple environment where the container is deployed. But when it comes to production, this is a whole different story. Running containers in a critical environment like production necessitates to use a runtime platform that takes care of extra functionalities or capabilities like security, repeatable deployments, scheduling, replication, HA, application updates, and load balancing. Developers and operations team want their applications to be super resilient, to be able to scale up when load increase and scale down when load decrease. And most importantly, they want to easily update their applications during business hours time with real-life traffic. Scheduled planned outage becomes a less desirable option today. The scope of the deployment is no more a laptop or a single server, but a fully distributed system with tens or hundreds or even thousands of worker nodes, and deploying the application should be always 100% reliable on this platform. Access to the application is done by leveraging a built-in load balancer, and security should be guaranteed at all levels, ranging from the platform access to data produced by the containers. The learning cliff is the terminology we have chosen to characterize the transition from containers in development to containers in production. The big misconception at the beginning of the container era was that once the container image was built, most of the work was done. In fact, the problem just got started. To fully enjoy the benefits provided by the container technology, all aspects depicted on this right side of the slide needs to be covered. Movement from monolithic to microservices architecture. Before going further, let's talk about microservices applications. Applications used to be monolithic from an architectural standpoint. It means a big pile of code was written by multiple teams to cover all the functions of the application, ranging from user access and management, front-end interface, application logic, database access, back-end integration, and so on. Major drawbacks of monolithic application are complex code maintenance, difficult regression testing, and the most obvious one, painful updates and upgrades. Microservices architecture is today more commonly used, and the key principle is to decompose the big application into multitude of smaller applications interacting one to the other over the network across different nodes. The smaller application is called a service and is constituted of lightweight code that performs perfectly well a dedicated function. Microservices application inserts itself into a bigger development process called DevOps. DevOps is not a product nor a standard. It is an organizational and technical process with the objective of accelerating the period from code commit to production readiness. The more faster an application can be deployed into production, the better it is for the company in terms of business. The more quicker an application can be fixed or updated, the better it is for customer satisfaction and retention. DevOps starts with a source code management tool like GitHub or Bitbucket, where developers push their code or fixes. It is a central repository for all the programming codes forming the application, and it can be branched into multiple releases. Once the code has been downloaded to GitHub, a trigger is sent to the continuous integration tool like Jenkins through a webhook activated on GitHub. The trigger requests Jenkins to copy the GitHub repository locally on the CI server. Files like Dockerfile, application code, and test codes are now available locally on the Jenkins nodes. Based on all these files and codes, Jenkins will start a job and build the Docker image from instructions contained in the Docker file. The other part of the job is to make sure this new Docker image passes all the required tests defined in the testing code spec. For this purpose, Jenkins will use a container runtime platform to deploy the container with the new application code and test it using instructions in the testing code. As you can see here, the container runtime platform happens to be Kubernetes. Enterprise IT stack is today composed of multiple technologies that rely on the lower layer to provide services to the upper layer. Physical infrastructure is at the bottom of the chain and typically provides hardware components like server, network, and storage devices. Virtual infrastructure adds a software component to the physical infrastructure to provide virtual resources like virtual machine, virtual networking, switch, router, and virtual storage. Then comes the IaaS layer, which provides a complete virtual infrastructure to a tenant by orchestrating and mixing all the previous virtual resources together. Platform services is built on top of the IaaS layer to provide an abstraction layer that allows application developers to deploy their code or container image in a very seamless way. Platform services typically provide built-in functionalities to ease the deployment and management of applications in production environments like scale-in, scale-out, upgrade assistance, service discovery, and HA. Application developers are now at the top of this IT stack, and they are the first-class citizens of this whole infrastructure. Everything was built here so they can consume it easily and produce great software for the benefits of the company. As we can see on the slide, containers and container schedulers operate at different levels on the enterprise IT stack. Container technology like Docker or Rocket from CoreOS operate at virtual infrastructure layer and more precisely inside a home called a virtual machine. Remember, container is an operating system virtualization technology. Container schedulers operate higher in the stack at the platform services layer. Container schedulers encompass projects or products like Kubernetes and PCS, Pivotal Cloud Foundry. Both are designed to work with containers as the base workload. Introduction to Kubernetes. So what is Kubernetes? Containers are revolutionizing the way we develop and manage applications. These containers allow to build, develop, test, and even deploy on the exact same system where the developer works. Layered file system can be used to fill in dependencies like libraries or additional required tools needed by the main application. Containers can even play a crucial role in zero downtime upgrade. This is fantastic until you end up with 5 different types of containers. Each of them need to be scaled out, and you need to get them to work together, discover each other, and upgrade together. This is where Kubernetes comes into the play. Kubernetes is an immensely popular open source container orchestration tool. It is an open source platform for managing, automating deployment, scaling, and operating containerized applications across a cluster of worker nodes. Kubernetes was originally founded by some Google engineers, and its development and design was heavily influenced by Google Borg system. The first stable version of Kubernetes, version 1.0, was released in June 2015, and it was considered robust enough to be running in production. At the same time, Google donated the code to CNCF, Cloud Native Computing Foundation, which is run by the Linux Foundation. Kubernetes provides the following capabilities. First, it will help you to deploy your applications quickly and predictably. Then it will allow you to scale your application on the fly. Over time, you can seamlessly roll out new features without disrupting the existing services. When deploying containers, you can limit the required hardware resources like CPU and RAM memory. In this sense, Kubernetes allows to optimize use of your hardware by using only the resources you need. And in case you need additional worker nodes to support the increasing number of containers running on the infrastructure, the scale-out operation is pretty simple to perform. Kubernetes is clearly a container orchestration platform, and sometimes you may see it referred as CaaS, which is the acronym for Container as a Service. One important point worth mentioning is that Kubernetes expects already built container images to operate. Unlike past platforms like PCF, you cannot inject source code directly to Kubernetes and request it to run the application. This is not going to work. What you have to do in advance is to build the container image using Dockerfile as previously seen, and then tell Kubernetes to run this image leveraging all capabilities provided by the platform. Container image is key here. Everything we have said so far with Kubernetes only apply when the container image already exists. Let's have a very high-level view of Kubernetes. First, Kubernetes comes as a cluster. Kubernetes is in reality a fully distributed platform composed of three main elements. The first main element is the master node. The cluster can be composed of one or multiple master nodes for HA and resiliency purposes. Master node form the control plane component of the clustering solution. Master nodes can be assimilated as the brain of the system. They control and dictate what other components of the system should do. The second main element is the worker node. A Kubernetes cluster can start with one worker node and scale out over time. Worker node is the data plane component of the clustering solution. Adding a worker node in the Kubernetes cluster is a straightforward operation. Worker nodes are under control of the master node and execute instructions set by the master node. The third main element is then the pod. Pod run and live in worker nodes only. A pod is the most granular unit of workload in a Kubernetes environment. Kubernetes schedules, manages, and operates pod elements. Many pods can be running on a single worker node up to the capacity of that node. Depending on the size of the pod, you can find 10 or up to 100 pods in the same worker node. In fact, this Kubernetes distributed system has some similarity with vSphere. Master node looks like vCenter. Worker nodes look like ESXi host. Finally, pods look like VM. For VI admin, this new architecture should sound pretty familiar. vSphere and Kubernetes are both distributed systems. vSphere, which means vCenter and ESXi host, manage VM, while Kubernetes manage pods. In practice, Kubernetes master nodes and worker nodes are usually instantiated as VM form factor. So you have this type of two-layer architecture approach with vSphere managing the Kubernetes cluster. Again, a Kubernetes cluster is a bunch of virtual machines. And then Kubernetes managing the pods themselves. Translated to this slide, imagine that VM1, VM3, and VM5, so the VM on the left side, are the master nodes, and the other remaining VMs are the worker nodes. So pods will then be running inside VM2, VM4, and VM6, which are on the right side. In this section, we are going to look at Kubernetes architecture and its core components. Kubernetes cluster consists of a master and a group of worker nodes. Again, multiple master nodes can be instantiated to make the overall cluster more robust and resilient. Kubernetes supports the concept of namespace, which is a mechanism to partition overall Kubernetes resources into logically named groups. On a fresh new Kubernetes cluster deployment, 3 namespaces are created by default: kubesystem, kubepublic, and default namespace. System-related objects, for instance, system pod like kubedns, belong to kubesystem namespace. Any objects created by user will lead by default into the default namespace. One of the main objectives with namespace is to provide multi-tenancy support for a Kubernetes cluster. Using namespace, multiple dev teams, development teams, or multiple projects can use a same and common Kubernetes cluster with full guarantee of independence and isolation. When creating a namespace, the superadmin can specify access and authorization for predefined set of users through the role-based access control functionality. Resource limits like max number of CPU and max memory size can be set and enforced per namespace. Once developers have their own namespace, everything they perform on the system lands into the namespace. Pods are created in this namespace. Services, replication controllers, replication set, deployments. All Kubernetes objects will be stored in this namespace. Namespace can be created and deleted on the fly. In practice, it is very easy to consume namespace with Kubernetes. I would like to add a comment about multi-tenancy with Kubernetes. In fact, there are 2 ways to achieve this. The first is by using the namespace construct, as seen before. The second is by deploying a new Kubernetes cluster and then allocate this cluster to a tenant. Each approach presents its own advantages and drawbacks, so picking one model versus the other is not always straightforward. Let's have a deeper look at the Kubernetes master node. First major component of master node is the API server. The API server is responsible to process user requests to the system. When a user interacts with Kubernetes through the kubectl CLI utility and asks for the deployment of a particular pod, the request will reach the API server for processing. Access to the Kubernetes system through the API server is secured and controlled. API server provides authentication and authorization using built-in mechanism or leveraging external authentication systems. API server also runs a set of admission controls that can reject or modify incoming requests. Not displayed in this slide, but API server is the only component that interacts with the etcd key value store, which is the central repository of Kubernetes cluster. Second major component is the scheduler. Scheduler receives requests from the API server and based on metrics gathered from worker nodes, has the responsibility to schedule pod deployment on a specific worker node. Scheduler is a plugin component, which means that if you prefer to develop your own scheduler, nothing prevents you from replacing the original scheduler with your own implementation. Dashboard, which is a web UI, is another component of the Kubernetes master node. The dashboard provides a web UI of the Kubernetes cluster and its content. Information like master nodes identification, worker nodes identifications, namespace, pods, services, and so on are displayed on the web page. The dashboard can also be used to create Kubernetes objects by injecting manifest files. Finally, the controller manager is the last component of the master node. Controller manager has the responsibility to keep track of desired number of replicas for a specific pod when instantiated with replication controller. Let's take an example. A user wants to run 5 replicas of Nginx pod. Kubernetes system will then deploy 5 pods. Each pod is running Nginx web server. Controller manager is now assigned the task of making sure 5 replicas of Nginx always run at any point of time. If one Nginx pod dies because the hosting worker node was powered off, then controller manager will see only 4 out of 5 replicas are running. As a remediation measure, controller manager will request the scheduler to schedule the missing pod somewhere in the cluster. Up then to the scheduler component to pick the right worker node. But at the end, 5 out of 5 replicas will always run for the Nginx pod. One interesting thing to note is API server is the central hub for all communications between scheduler, controller manager, and kubelet. We will see this component later in the next slide. Controller manager does not interact directly with scheduler. Communication is done through the API server. One of the reasons for API server to be the central point of communication is because it is the only component that interacts with the etcd key value store. This guarantees integrity of the Kubernetes system. Let's have a look at the worker node now. First major component of worker node is kubelet. Kubelet is an agent that only interacts with API server on the master node. It is constantly watching for pod spec instructions to determine what it is supposed to run. Based on the order initiated by the scheduler component on master node, the request will flow through the API server down to the kubelet on the worker node. Kubelet will then execute and schedule the required pod on the local worker node. kubeproxy is the second component of worker node. kubeproxy is a daemon watching the Kubernetes service object on the API server and implements east-west load balancing on the worker node using IP tables, leveraging NAT and filtering capabilities. kubeproxy is somehow assimilated to the network component of Kubernetes and only lives in the worker node. It is a critical component for pod-to-pod or external-to-pod communications. When user creates a Kubernetes service object, kubeproxy is responsible to translate that object into meaningful rules in the local IP table of the worker node. IP tables is used to translate the virtual IP assigned to the service object to all the pod IPs mapped by this service. This is why we mention NAT here. Finally, the last component on the worker node is the container runtime. Container runtime is responsible to pull container image from public or private registry and run the container based on this image. Kubernetes supports major container runtime like Docker and Rocket from CoreOS. Kubelet interacts directly with container runtime to start, stop, or delete containers. etcd is a simple, distributed, consistent key value store of Kubernetes. The content of the store is a set of entries containing key and value. The strength of etcd resides in its high performance in terms of access to the data. etcd provides a very interesting function which gives the ability to watch for a particular key and to be instantly notified if the value changed. etcd provides a REST API for create, read, update, delete operations, as well as an interface to register watchers on specific keys, which enables a reliable way to notify those watchers when the value changes. This watch mechanism is fully leveraged by the API server to be notified upon change of critical key fields. etcd stores configuration data that can be used by each of the nodes in the cluster. An example of data stored by Kubernetes in etcd is job being scheduled, created, and deployed, pod, services, details and state, namespace, and replication information. etcd is usually deployed in cluster mode with multiple nodes, 3 minimum, to guarantee HA and resiliency. etcd is also used for service discovery in a Kubernetes environment. Let's go into some details here. When a Kubernetes service is created, it is created with a set of label selector. The selector generally contains a set of labels that will be used as criteria for mapping the service to the pod. When a pod is created, extra information or metadata can be added to the pod. In this occurrence, the metadata contains one or more multiple labels. If the pod labels match with the service label selector, the pod will then be mapped with the Kubernetes service. This mechanism is used by Kubernetes for service discovery, and all this computation is done through etcd key value store thanks to this metadata that the data store is able to manage. Finally, etcd represents the state of the cluster that each component on the master or worker node can reference to configure or reconfigure themselves. etcd globally holds the exact cluster state and can be seen as the trusted primary reference data or source of information. In this section, we are going to cover Kubernetes basic concepts. Pod is the atomic unit of deployment in Kubernetes. It is the most granular unit of workload that runs on the platform. A pod is a composition of one or more containers. When dealing with Docker, we talk about containers. However, when working with Kubernetes, we have to deal with pod. Pod is created using a manifest file that is submitted to the API server for processing. In this manifest file, which comes as YAML format, one or multiple container images one or more multiple container image needs to be mentioned. In this slide, we show two pods. Pod 1 is composed of two containers. Container 1 runs Nginx, and the Docker image was built based on an Ubuntu-based image. Container 2 runs Wavefront, and the Docker image was built based on the Alpine-based image. Pod 2 is composed of two containers. Container 1 runs Redis database. Container 2 runs Wavefront. Both pods are here using the same Docker image for the Wavefront container. Some other rare case scenario to support multiple containers in a unique pod is for logging and monitoring or for service mesh. In the case of logging and monitoring, a sidecar container can be leveraged for logging or management purpose. This sidecar container runs alongside with the main container. In the case of service mesh, a sidecar container is used to police and control all the traffic going in and out of the main container. Having the capability of running multiple containers inside a unique pod in reality opens the door to a multitude of new capabilities for developing and managing cloud-native apps running on the Kubernetes platform. Containers within a same pod are inseparable. Containers that belong to a same pod are always scheduled on the same worker node, and the pod is considered up and running only when all its containers are up and running. It is not possible to find a situation where containers that belong to the same pod are scheduled on different worker nodes. The group of containers that form the pod live together and share the same destiny. When the pod is deleted, all the containers are deleted. When a pod is created, all the containers are created. One important point to mention here, a pod never resurrects. What I mean here is when a pod is deleted and then recreated, the new pod does not necessarily keep the same attributes than the previous one. The new pod may be scheduled on a different worker node, and IP address of the new pod may differ from the previous one. Even worse, the dynamic name of the pod will certainly change. Containers within a pod share a same and unique IP address. If they need to talk one to the other, they can use the localhost mechanism. If different containers inside the same pod provide services over the network, they need to use different TCP or UDP ports. In a Kubernetes cluster environment, pod IP address is unique. So far, one pod has only one IP address. Each worker node is assigned a dedicated subnet for pod IP allocation, which means that every pod living in the same worker node belongs to the same subnet range. For instance, worker node 1 is allocated with 10.200.0.0/24, and worker node 2 is allocated with 10.200.1.0/24. So the pod scheduled on worker node 1 will have 10.200.0.x/24 IP address, while pod scheduled on worker node 2 will have 10.200.1.x IP address. One key design principle of Kubernetes since day one is that pods should have a unique IP address cluster-wide, and each pod should be reachable by using simple layer 3 routing. Containers in a pod also share the same volumes. The key benefit here is if one container writes data to the volume, the other containers can read uniformly this data. At this point in time, it is really important to remember that containers from a same pod share both the same network and storage characteristics. Lastly, pods are considered to be ephemeral, just like containers are. When the pod is deleted, the allocated default volume is deleted, and the IP address is given back to the pool for new allocation. To close on this slide, it is tempting to assimilate a pod with a VM. A pod has an IP address, has a volume for storage, and when a pod is scheduled, developer can set the CPU and RAM resources allocated for this pod. But don't be misled here, because a pod is by nature ephemeral and immutable, in the sense that its containers are instantiated from a fixed image. Pods usually don't live for a very long time, and nobody will ever log into a pod to update or upgrade its code. In case a new version of the application must be deployed, the process is to build a new container image and then deploy associated new pods alongside with the existing one to guarantee a smooth transition. So a pod is not a VM. Label is a metadata and consists of a key value pair attached to pods and convey user-defined attributes. Label is a very simple concept, but at the same time, very powerful in Kubernetes environment. In fact, labels can be set to any Kubernetes object: pod, services, replication controllers, node, deployment, and so on. The key value pair is totally free in terms of content. For instance, as shown in the slide, pod 1 can be labeled with two key value pairs. The first one is tier equal frontend. The second is app equal my app. It's easy to understand that this pod belongs to the app named my app, and its function is related to the frontend. Pod 2 is also labeled, and we know it belongs to the same application, but its function is related to the backend. The question is now how to use those labels. The answer is you can use label selectors to select pods with particular labels and apply services or replication controllers to them. For instance, we can create a Kubernetes service object called frontend with label selector tier equal frontend. Because pod 1 contains this label, it will become an endpoint of the service frontend. Same mechanism applies if we create a Kubernetes service object called backend with label selector tier equal backend. In this case, pod 2 will match the selection. The very nice thing with labels in a Kubernetes environment is its dynamic nature. Labels can be attached to objects at creation time and subsequently added and modified at any later time. Services are replication controllers that use label selector to match pods are refreshed in real time when labels are imposed or modified on pod. For instance, if we change pod 2 with label tier equal frontend, pod 2 will immediately become an endpoint of the service named frontend, alongside with pod 1. Label can be used to define affinity for worker nodes. If you have, for instance, 3 types of worker nodes having different characteristics in terms of CPU or memory or disk, you can create 3 labels, one for each type of server. For example, label 1 will be server equal gold. For server 2, label server equal silver, and for server 3, label 3 equal bronze. When deploying a pod, you can now use these labels as a way to influence the scheduling over the working node. If your pod is labeled with server equal gold, you can be sure that the pod will land on the worker node imposed with this label. Persistent volume provides persistent data storage for pods. Persistent volume and persistent volume claim was designed to be compliant with separation of duty requirements in an enterprise organization. The cloud admin owns the responsibility of operating and managing the Kubernetes cluster or platform. The developer owns the responsibility to write bug-free code, and he should be able to easily request access to persistent storage volume for his or her application. So in this model, the cloud admin has to provision in advance a pool of persistent volume using any available data store type. Data store can be vSAN or VMS or VMFS or NFS. On top of this, cloud admin can specify different storage class like gold, silver, and bronze, depending on the performance of the underlying data store technology. For instance, vSAN with SSD as capacity disk can be assimilated with gold storage class. Then, cloud admin has to register the persistent volume for availability in the Kubernetes system. At this point in time, the pool of persistent volumes are ready for use by the developers. To use a persistent volume, developer has to raise a claim when creating the pod. The claim should contain the capacity in terms of size, usually in gigabytes, required by the pod. If there is still enough available space in the pool of persistent volume, the claim will be granted, and so the pod will be able to use the persistent volume to write and read persistent data. The developer can also opt to release a volume claim in case his pod does not need any more access to this precious resource. Once the persistent volume is released by the developer, the volume goes back to the available pool. This is the reclamation process, as shown in the slide. If a different developer needs to access a persistent volume for his or her pod, the same process with claim and allocation will apply. After pod, I would say that service is the second most important concept of Kubernetes. One key principle with Kubernetes is that pod never talk directly to another pod, and external users never interact directly with pod. If this is the case, well, the application design is bad and needs to be reviewed. Pod talks to another pod using an abstraction layer, which is the Kubernetes service object. The same applies for user to pod communication. Kubernetes service is materialized by IP tables and all its filtering and NAT rules. Each worker node in the Kubernetes cluster has the exact same view and instantiation of the Kubernetes services that has been created from the API server. It means IP tables, filtering, and NAT rules are identical across all worker nodes. Kubernetes services contain endpoints, which are the set of pods matching the label selector criteria. Remember that when you create a Kubernetes service, you typically specify some label selector criteria. If the pod contains labels that match the label selector, well, the pod will be part of the service. Or another way to say this is the pod will become an endpoint of the service. On the right side of the slide, we show that Kubernetes service named service has 3 endpoints, pod 1, pod 2, and pod 3. There are 3 services types you can use when creating the Kubernetes service object. Cluster IP is for pod-to-pod communications. All communications reside inside the Kubernetes cluster. Node port is used for user-to-pod communication. In case a set of pods are designed to be the front end of the application, you need to create a Kubernetes service object with type equal node port. What Kubernetes will do is to allocate a dynamic TCP or UDP port between 30,000 and 30,767, and to access the service, you have to use the worker node IP address appended with the dynamic TCP or UDP port. Of course, the worker node IP address needs to be routed in the enterprise network for this to work. If you look at the diagram, the way to reach our application is by using the IP address 192.168.10.10 and using the port 41,233. Finally, load balancer is the last service type and is built on top of the node port service type. In this situation, when you create a service with type equal load balancer, Kubernetes system will deploy a dedicated load balancer instance to access this service. The load balancer will have a virtual IP address that user needs to reach to in order to access the underlying pods. How does it work? Internally, the load balancer will use the node port mechanism to load balance the traffic to the worker node using the dynamic TCP or UDP allocated port. Once traffic reaches the worker node will perform a lookup in its IP tables to find the endpoint of the service at east, which means the correct pod IP addresses. Kubernetes service is the main building block for service discovery capability with Kubernetes. When you have a microservices application with hundreds of services interacting one with the other, you need a mechanism to identify and register all these services. This is called service discovery. In the case of Kubernetes, service discovery using a built-in DNS server called SkyDNS. It will soon be replaced with CoreDNS for information. The DNS server runs as a pod in the kube system namespace. When you create a Kubernetes service object, an A record is automatically created in the DNS server. On this slide, the service name service1 has been created, has an entry created in the DNS server with DNS name equal service1.cluster.local, and the IP address is 10.2.3.14. Note the IP address here is an arbitrary IP picked from a predefined IP pool, and this IP does not need to be routed in the corporate network. In fact, this IP address has no real connectivity. The key point here is the IP will never change over the life of the Kubernetes service object. This IP will be used by IP tables to perform NAT translation to find out pod IP address. In this case, IP 10.2.3.14 will be translated to IP of pod 1 or pod 2 or pod 3. Service discovery is extremely powerful while at the same time easy to use. If front-end pod needs to communicate with a DB pod to store some user data, for instance, the front-end pod will use the name of the service, for instance, db-service, to request access to the database. Because all pods in the Kubernetes cluster will use the same built-in DNS server, SkyDNS again, the service name will be translated to its IP address, something equivalent to 10.2.3.14 here. Packets will be sent from the pod to this IP address. A lookup is performed in the IP tables, and the NAT entry for this IP will return IP address of the DB pod. In fact, any DB pod that is an endpoint of the service named db-service. The loop is closed, and the front-end pod has successfully communicated with the DB pod even without knowing anything about this pod. Only thing that mattered was the service name. Replication controller is an extremely valuable functionality in Kubernetes to make sure a desired number of replicas for a selected pod is always up and running. Replication controller is fully managed by the controller manager component in the Kubernetes master node. Keep in mind that Kubernetes allows to define manifests in YAML format that reflects the desired state of the desired state of the user. Kubernetes will then make its best to conform with this desired state by adjusting the real state with the desired state. Kubernetes will most of the time make sure that real state equals desired state depending on the available resource in the Kubernetes clusters. So if a user needs to have 10 front-end pods and 4 back-end pods always up and running to guarantee a fully operational application, well, Kubernetes will make it happen. Let's see all the capabilities of replication controller. Replication controller is used to manage auto-healing situation. If a pod dies, replication controller will detect the event and then create a new pod to replace the disappeared one. Replication controller allows to manually scale in or scale out number of replicas for a selected pod. In case of front-end pod, user can easily increase or scale out number of active pods during peak hours and then decrease or scale in those pods when no more needed. Replication controller can be used for application upgrade. We call it rolling update in this case. Replication controller provides the capability to roll out new pods with the new image version while maintaining old pods with the old image version. By playing with the service label selector, traffic can be seamlessly redirected to the new pod. Once the new pods are considered to be stable enough, replication controller can then suppress any old pod living in the cluster. Lastly, replication controller allows to run and track multiple releases of the application. A replication controller is intimately mapped to a specific set of pods running the same image version. And Kubernetes allows to create as many replication controllers as needed. Let's see the replication controller in action. User has submitted a manifest file to the API server requiring 3 replicas of pod running image 1, let's call it pod 1, and 2 replicas of pod running image 2, let's call it pod 2. API server receives the request and informs the controller manager component about this new replication controller object. Controller manager takes into account the user need and asks the scheduler component to schedule those total 5 pods across available worker nodes. The result is shown on the slide, and pod 1 replica 1 is running on worker node 1, while pod 1 replica 2 and pod 1 replica 3 run on worker node 2 and worker node 3 respectively. Pod 2 replica 1 is running on worker node 2, while pod 2 replica 2 is running on the last worker node. As mentioned before, user declares the Kubernetes system a desired state, and Kubernetes will make sure the real state match with the desired state. Now, user submits to the API server a new request for 1 additional replica of pod running image 1 and 2 additional replica of pod running image 2. Again, Kubernetes system will instantiate the required pod as needed. As you can see, for now, we have 4 replicas of pod 1 and 4 replicas of pod 2. So far, so good. Now an outage occurs on the second worker node. The server has been shut down or powered off, for instance. All the pods living in the server are now gone. The master will detect that worker node 2 is down thanks to the periodic beacon prop from API server to kubelet. API master knows the worker node 2 is down and will inform the controller manager about this event. Controller manager manages all the replication controller created in the system and knows exactly how much pods are desired and how much pods are actually running. In this case, the controller manager understands that 2 replicas of pod 1 are missing in addition to 1 replica of pod 2. A repair measure is triggered and the scheduler component is asked to schedule the missing pod onto available remaining worker nodes. At the end of the operation, we have back sorry. At the end of the operation, we have back 4 replicas of pod 1 and 4 replicas of pod 2 again. Kubernetes will make sure that desired state equals real state no matter what. Replication controller was introduced with the early release of Kubernetes. Although it is still available, people tend to use now replica set, which is an evolution of the replication controller and offers new capabilities like more complex label selector rules using match expression. Replica set is the next generation replication controller, so you will certainly hear more about replica set. However, everything we have explained so far with replication controller can be applied to replica set. So I need to plug my laptop because I have no more battery. So I will be back in just 1 minute.
All right. Charlie, are you on the line?
Stateful sets. As we have seen before, Kubernetes supports both stateless and stateful applications. By default, when a pod is terminated, all its data are wiped out. If the pod is created using a persistent volume through the persistent volume claim process, any data written in the persistent volume remains alive even if the pod is terminated. Stateful set goes one step further and provides stateful capabilities for clustered type of applications like high available database workloads. Stateful set enables running pods in the cluster mode. For instance, if you want to deploy a cluster of MySQL instances with active or active standby configuration, you will need to leverage the stateful set construct. Stateful set was initially called pet set, and as the name suggested, the intent was to manage the set of pods like a set of pets. It basically extends the concept of replication controller or replica set to stateful pod. So what does stateful set do? It launches multiple replica of pods using the same image in order sequence. To be more exact, it manages the deployment and scaling of a set of pods and provides guarantee about the ordering and uniqueness of these pods. You can specify as many replicas as you want. So pod 1 will be created, then pod 2, then pod 3, and so on. The value proposition of stateful set is it maintains a kind of sticky identity for each pod across the whole lifecycle of the pod. Each pod has a persistent identifier that is maintained across any rescheduling. In a stateful set, the pod is recreated with the same name and properties to maintain a consistent identity. Thanks to this characteristic, if you allocate persistent storage to these pods created using the stateful set construct, you have the guarantee that if any of those pods goes down and needs to be rescheduled, the new replacing pod will keep the same identity than the previous one and will access the exact same persistent volume than the previous one. A requirement of a stateful set is satisfying the network identity of the pod. To do this, a standard Kubernetes service must be deployed using the selector and app to identify the logical mapping to the stateful set. The headless service is for pod-to-pod communication. Each pod gets a DNS name server. Each pod gets a DNS name accessible to other pods in the set. On the side note, as shown in the slide, pods are created in sequence. However, when pods are deleted, the reverse sequence applies. The last pod to be created is then the first one to be deleted, and so on. Finally, we mentioned MySQL initially, but please remember that stateful sets are really useful to deploy other applications like Zookeeper, Cassandra, etcd, and so on. We reach the last slide of the presentation, and it deals with daemon set. Daemon set allows to run a unique copy of a desired pod on every node in the cluster. This particular pod can fulfill any task useful at worker node level, like monitoring, log collection, security. Pod providing centralized services at the worker node level is the perfect candidate for daemon sets. Anytime you insert a new node in the Kubernetes cluster, the scheduler will automatically create a daemon set pod on this new node. And when the node is removed from the cluster, or when the node is simply down, the daemon set pod is not rescheduled anywhere else. This is the key differentiator with replication controller or replica set, as they would reschedule the pod in that case. So let's see daemon set in action. So daemon set pods are scheduled on each of the worker nodes, and if worker node 2 goes down, the daemon set pod is not rescheduled anywhere else. This concludes my presentation. Thank you for listening, and I hope you enjoyed it. Thank you.